Good to me.
I say. All right, sorry. And the topic of the first presentation is hardware offload with Open vSwitch and TC Flower.
Yep, okay. Perfect.
To you.
So thank you. So welcome everybody. My name is Eelco Chaudron. I do work for Red Hat as a software engineer in the networking team. And today's talk is going to be about, like you said, OVS and some hardware upload, the benefits, and if you really need it or not. So the first thing we should probably ask ourselves is why are we using or how are we using OVS in the infrastructure? And this is a picture from the Open vSwitch website, and we're going to use it to focus our task environment on. So we have virtual machines that talk to the Open vSwitch, and that will be routing the traffic back and forth to the devices. The main goal here is to see where we need hardware offload. So trying to compare it to like the kernel data path is not really a reasonable comparison, because the kernel data path is pretty slow compared to the user space data path. So what I'm going to do in this presentation, I'm going to compare it to the user space or the DPDK data path for Open vSwitch. And what I'm going to do is I'm going to use the physical to virtual to physical test, as we used to call it internally, or PVP test. In our scenario, we use the PVP test on a single arm, which means that the same physical port is used for ingressing the traffic as well as egressing the traffic. You see a lot of other PVP tests where they use a different physical port for ingress and egress, and also a different virtual port for ingressing and egressing. This distributes the load between two different ports, and our example is to fully load a single data path. We have a homegrown Python script that we use to test this scenario. The link where it's available is there. This is not a zero packet loss type of test, so we will send the packets at wire speed, and then we just measure the amount of data that's dropped. If you like to test yourself and you would like to do a zero packet loss test, according to our C specifications, you probably want to go and try to use vSperf, because that is set up for that scenario. That is using two physical ports rather than one first physical port for the testing. And then I think that is really important if you really would like to compare your hardware offloads against your own environment, that you really go ahead and test it against your environment. Because with what we see, if you do some testing, you can really manipulate the test to be really in your advantage. So if you have a specific need for your test, for your environment, tested in that environment. Because what we see, the factors that actually change it is that if you have many flows in your system, it will actually affect the performance, because it needs to look up more flows in your environment and you get slower responses. Also, the kind of open flow rules might differ. So if you have rules where you would actually match to an ingress port and directly send it to an egress port, it's less processing in that scenario as well. Then, of course, the important part that you see with the DPDK part is the EMC caching and the receive and transmit batching in that scenario. So if you have a lot of different flows sent, the traffic pattern itself is really important. So if you have like 6 active flows and maybe 1 million flows that exist in your network, if only 6 active flows are walking around, flowing around, it will not trash your EMC cache. And that will be a different thing. When we look at some of the numbers, you can easily see the difference if you have multiple flows. So if you go above 10 flows, and I try to explain in that slide a little bit why that is the issue. Yeah, and then of course the actions that you take also affect the performance. So if it's just a forwarding action where you say come into a specific port and go out to a virtual port, that is way less action than if you need to pop and push some VLAN labels or add some additional tunneling or extracting it. So what have we done for the reference test in our scenario? So we have an Intel system, single CPU system. We use Open vSwitch 2.9. I think the reference is about 2 or 3 weeks old, master branch. DPDK 1711. For our reference, we use one core, which consists of 2 hyperthreads, only for the forwarding of the traffic. And then with that, we have 2 queues per interface, which are both pulled by the same PMD thread in our environment. So we have test PMD as the loopback. We're not changing any of the traffic, so we loop back the traffic as it is. So it comes into the virtual machine, and we send it out the same virtual port on the virtual machine. Let's see. So the traffic is very basic traffic, is UDP traffic, and we only change the source and destination IP addresses, so we have at least a distribution around our RSS feed. And then I'll show the number of traffic rules, the number of traffic flows that we have. So if I say we have 1 million traffic flows, that means we have 1 million variations of the source and IP addresses. Because we have a rule in each direction, so going through the virtual machine and coming back to the virtual machine, we have the double number of open flow rules. So if we say we have 10 traffic flows, that means we have 20 open flow rules in the system program. And more details, we have a blog post on our developer site where you can have more details on what the setup is like and what you can change. So this is what we get when we are running DPDK a scenario with 2 cores doing PMD. Here you see the number of flows, so 10 flows, 1,000 flows, 10K, 20K flows in the traffic, which means the double number of open flow rules that we have active in the system. And you see a huge difference between the very low number of flows, the 10K flows, and when we increase the number of flows. And there is a reasonable explanation for that, is that in the DPDK scenario, what they do, they try to batch packets that are ingressing into the system. So let's say you have, they do a batch of 32 packets. So 32 packets at a time are taken from the NIC hardware. So if you have the 10 flow scenario, that means if you are batching, you will at least have 3 flows that are 3 packets that are from the same flow. So in that scenario, DPDK, what it does, it batches those 3 packets together and then sends those 3 packets out in one go to the same destination. So that is less requirements on pushing it to the next hardware. So you can directly push 3 packets to the hardware in one go. Versus if you have more flows, so if you go for 1,000 flows, that means all the 32 packets that come in and then grab from the hardware all are sent individually to the hardware. So basically you access the hardware 3 times and you say send those packets, send me 1 packet for this flow, then send me 1 packet for the next flow. Whereas if you would batch them, you would say to the hardware, here you have 32 descriptors, go ahead and send all 32 of them to me. So recently there has been some enhancement going on upstream that we worked on that actually allows not to do the batching, the transmit batching based on the ingress flow, but it does the batching based on the egress flow. So what it does, it takes all the packets into a queue, all the 32, processes them like they need to be processed, and then it batches them based on the egress port. So if we would run the PVP scenario in this case, and you would have that fix applied, because all the packets that are ingressing from the same NIC egress on the same NIC as well, you will see that even for the multiple flows, these numbers are way higher and almost close to the 10K one. So that's one of the reasons why I say if you're going to test something for your environment, test it like your environment. So not only the number of open flow rules in your environment, not the number of PMDs, not number of cores, but also try to mimic your traffic pattern as best as you can, because the traffic pattern really affects the way the packets are sent out on the egress side, or at least are moving through your network. So this is a 10 gig NIC. So you can see we're heading about roughly 4.5 million packets a second. The next slide I have is where I actually have the theoretical maximum of the 10 gig inserted. So what you see here is that we're not even getting close to 10 gig with 1 core. You see roughly around, For the low flows, roughly around 512 packets, 500 packets we get close. For an average flow, which in a real network probably is around this number, around 1,000 maybe, you see that to be wire speed, you roughly need to be roughly around the 1K to 900 byte packets to get wire speed. The next graph illustrates, and it's probably impossible to read, sorry for this, but it's the CPU usage. So like we said, we have 2 cores dedicated for the PMD processing, which means we lose 2 cores out of the number of cores that you have in your system for doing the real work. So that's what this graph is trying to illustrate. So we have 2 PMD cores, so we have roughly 200% of CPU usage. You see if the flow increases a bit, you see there is a bit of overhead, and that is the revalidators trying to see if the flows are actually being used in your network or not. To see where we actually lose the packets in our example, is what I have here is a bit of a, the script gives you at the end the results of your specific test. So this is for the 10 flows. It tells you how many packets it actually sent by the tester, and then you can see where you lose them. So for the DPDK, the most part we lose on the physical interface, because in the physical interface they come in wire speed 10G, and we drop them there. And the reason is we only assign 2 PMD threads. So if you would assign more threads to actually pull the hardware or the hardware queues, you would lose them. So it's pretty clear that we lose them on ingressing. You see we also lose a bit on the virtual machine here. And the reason probably if you would assign more cores to the virtual machine, we might be able to pull up more of them. We might also be able to give a little bit more receive buffers and to make the number a bit lower. But in the end, the main issue here is also the polling. So in theory, if you would add more cores, you will get less packet through. So that's what I'm trying to do here. And this is pure theoretical calculation. So assuming that we would scale on a linear base if we add more cores to the system, we get roughly 4.5 million packets per second. So for 10 gig, we need over 14 million packets per second. So if we simply divide the number of cores, we see that we roughly need 3.2. So let's say 4 cores to process 10 G of data at the minimum 64-byte packets. And of course, it's not really true, because we take the best case example where we only have 10 flows in the system. So if we have the 4 cores, that means we should distribute them all around with RSS. So that means we can probably only in that thing sustain 40 flows, which is nothing. 40 TCP sessions that we're trying to track is really minimum. Also, in the real life, the network doesn't consist of 64-byte packets. I mean, there is a huge variation of packets. But what I'm trying to say here is at least the killer in this scenario is the number of flows. You saw it if you go to 1,000 flows, it really drops. It drops down. And then what about 25, 40, and 100 gig? Well, you can see you need a lot of cores. And those cores are real cores. So basically this means 13 cores means 26 hyperthreads if you really want to sustain it. So there is no really a CPU where you can find enough of those cores to actually do something with the workload once you get it up to the CPU. And you need your virtual machines to have some load as well. So, and this is not even taking NUMA node into consideration. For DPDK, your CPUs should, or your NIC should be on the same NUMA node to get even a decent performance. So if you try to move your VMs on a different NUMA node, but have your hardware, the NIC on another NUMA node, your performance really goes down the drain. So for real traffic, even for 10G, if you want to really do NFV type applications, you better offload. I mean, it really helps you save the CPU cycles. So what is the solution for this is the hardware offload. So with the hardware offload, we probably want something like this. So basically we have the NIC on the bottom that has a virtual switch which can do traffic classification and steering for you. And then you also want the virtual machine to directly access that hardware, because as soon as you need to first get the packet into the kernel and then have the QEMU or your virtual machine touch it, there is a lot of steps in between, and it will probably drop your performance quite a lot. So the solution the hardware vendors came up with is they have an internal switch. So the packet comes in on the physical port, they do some magic here by matching traffic patterns. And then they forward it to a virtual function internally inside their system. And then the virtual machine basically accesses the PCI bus directly over SRIOV, and then takes the packet up to his own user space or to his own memory, and then can use it. So in our environment, we use test PMD, which is also a DPDK application. So it directly takes the data from the PCI bus and uses it and loops it back into the interface. There are some disadvantages to this platform as well, to the solution. I think the main problem is that, what is it? What do I have first? So it needs to stay on the NIC. So as soon as you go off the NIC, and it needs to go to a different virtual function or to a different piece of hardware, you lose the benefit of the hardware offload, which is a pain. Exception traffic takes a slow path, meaning if the traffic cannot be matched by the hardware, it still goes to the kernel for further processing. And what I've seen with some of the vendors is that that exception path is slower than the normal data path. So it's really an exception path. So the traffic goes there and it's going to be processed by the kernel, but it's not at the same rate as a normal network interface might be. And then the other thing is redundancy and live migration. Because in the picture, go back one picture, you can see the virtual machine directly talks to the PCI bus. So it directly has all the status and registers on the PCI bus. So if you would like to move this virtual machine to a different piece of hardware, you lose that direct connection. So even if you would have set up your QEMU on a different system with the same kind of NIC, you still need to integrate, somehow do the transition. There are people working on solutions for that, but currently with the current implementations, it doesn't exist. So you're really bound that you're not really hardware agnostic in the sense that you can move from one machine to another. Also, the redundancy and the bonding is an issue. You need to move to a different model because normally you would have bonding maybe on two physical NICs, and then you would bond there, and then you would go to your virtual machine with a single interface. That won't work for the same reason, because if you go to a different physical machine, you would duplicate this part here. But you cannot do the bonding here because if it comes in on a different NIC, there is no direct path to the virtual machine. So what you need two smart NICs on your system, and then you would bundle this interface as a bond to the virtual machine. So the virtual machine will get two interfaces, both into one of the smart NICs to get the same redundancy if you had before. And the other limitation is the number of actual virtual machines that you can use. So depending on the hardware vendor, you might have a limit of 64 VFs that you can create, which means you can have 64 virtual machines that use the hardware accelerated data path. So what is Open vSwitch approach to this? So they have added the hardware NICs support since 2.8, which is based on the TC Flower implementation of the Linux kernel, which is available in 4.2 roughly. That's what currently is available. They're planning actually upstream to also have support for the DPDK data path. There's discussions going on at the moment, and there is two different approaches that they're working on. So there is the partial offload solution. If you analyze the DPDK solution in general, you see that a lot of CPU time is actually spent on calculating hashes and figuring out which flow to match. So with the partial offload, they try to offload that to hardware. So the hardware is doing some of the partial matching, some of the matching for you, and it gives you an identifier saying, this is probably part of flow XYZ. And at that stage, Open vSwitch only has to look at the identifier and can quickly get whatever rule it needs to apply, and then applies the action and can send the packet out. Just it saves some time. And then they're also looking into a full offload, and that is what they currently do with the TC Flower implementation. So hardware takes care of the packets, gets them ready, and then sends them out on the hardware directly to the virtual machine. So what is TC Flower? So TC Flower is a classifier that is used in Linux And what they have added there is they had added the option to match and move the rules to hardware in a specific case. And this can be done, it's a general infrastructure, but currently only Flower is the only one that implements the backend for it. So your network interface card, what it does, if it supports hardware offload, it can register itself to Linux and set with the function call tc setup callback edge register. And then whenever there is an event, an add or a delete of a Flower rule, it gets an event by any of those 3 messages. And at that stage, the hardware can start try to program whatever is needed for the hardware, and then it will take care that whenever a packet hits the same Flower classifier, it's processed in hardware, or at least the actions are taken that we give into it. So from a software perspective, the TC Flower is nothing else than a classifier in any other classifier in the Linux system. So you can assign all the actions that you could normally assign to any other of the classifiers. The only thing that really stops you from using it is the implementation of the hardware. So the hardware is free to match and support whatever match actions it wants to support. And it's also free to support any of the actions that is been given. So when it receives the callback for the replace, which basically is for adding or replacing the Flower entries, it can either say, okay, I'm happy, I can take this entire rule in hardware and I start processing it, or it can tell, I have the entire rule, but I cannot do anything with it, and then it will just not apply it. So it's either one. So you either apply the hardware rules and you are processing them, or you cannot process them. And then Flower has 2 actions added to it, which is skip software and skip hardware. So if you do nothing and you just enter your Flower rule, it will be programmed in hardware, or at least it tries to program it in hardware, and it will try to program it in software. So you have a fallback mechanism. So if for some reason the hardware is skipping it or is not catching it, the software will pick it up once it comes to the kernel data path. But you can also say, I don't want the hardware to be programmed. I just want it to be software for this specific rule. Then you can apply the flag and you say, okay, even if the hardware match is capable of matching it, I don't want the hardware to do anything with the packet, just send it up to software. And vice versa. You can also say, if you would like to be testing your stuff, you can say, okay, skip the software part, and if it comes to the kernel, I'll just do the normal forwarding. So that is the preferred way for Open vSwitch, but it's not the default way for Open vSwitch. We'll talk a bit when we're configuring it, why that is the case in that scenario. So from a Flower perspective, this is just a quick cut and paste from the man page. So it supports matching on the most common fields, like all the IP fields, some Ethernet ports, and there will be a lot of things are added there because people are looking into adding more MPLS and other tunneling protocols. So this Flower is really, if you look at upstream, it's almost changing on a daily basis. People are trying to add more matching criteria for it. And like I said before, it really depends on the hardware if it's supported. So some hardware vendors might support all the tunneling options or IPv6, and some vendors might not support it. So it really depends on the vendor that you select. So if you're doing testing, if you would like to buy one of those cards, make sure it fits whatever your needs are. So the actions. So the actions are from the general TC framework. So it supports all the actions, or you can configure all the actions, but it depends on the hardware what actions are supported. From an Open vSwitch perspective, at the current stage of 2.9, these are the sort of actions that it supports and uses. So it uses the drop and redirect action, and then the checksumming, some packet modifications for tunneling, and then some VLAN push and pop. But it's whatever. So OVS will still try to push it down. If your hardware doesn't support it, it will not be part of the rule sets in the hardware. And there are flags to see it. So in general, you can enable or disable the offload features globally on the NIC. So if you want, for some reason, to test something and you say, I would like to disable everything on my NIC, there is a command to disable it using the E tool. You can also use the tool to see if you have support for hardware, because it will show up as a hardware offload flag. And if it's not supported, we'll have the fixed variable there saying, you know, the NIC doesn't support hardware offload. I think an important thing to note is that a lot of vendors, when they do TC offload, it changes the mode of the network interface card. So you either use the card in like a TC mode, or you use the card in a general networking mode. Some vendors require you to have special firmware installed, or switch the firmware to do that. So you have to be careful if you actually go that route to make sure you have the right software for the vendor installed. So adding a simple rule, if you want to do some testing without anything OVS, you can just install a rule using the TC. This example just adds an ingress rule for all ICMP traffic. And I added the flags skip software. Basically, program it in hardware, don't program it in software. So if for some reason the hardware fails, it will still come up to the kernel and it will follow the normal processing path of the kernel. If you would remove the skip software, then the software would still drop the packet for you based on the TC rules. So how does it look like if you view it? I think for troubleshooting this is nice because the commands still work. If you have OVS environment, you can dump all the rules that OVS put into TC. And I think the interesting flags here is the in hardware flag. So if the hardware decides that for some reason it cannot add it in hardware, it will report it back. And you can see it here in when you dump the rule. So that's nice for troubleshooting. So that's why I put it here. And it will also show any of the other configuration flags that you put here. And of course, statistics. So what happens with statistics is to take into note is that it will pull the hardware frequently to get the statistics. So your statistics might be behind a little bit. But it depends on the driver implementation, how fast that is. But this is a total sum of both the hardware and the software. So they accumulate both of them. Unfortunately, I was hoping that we would have a separate counter for hardware and software. It might be useful for troubleshooting, but currently that's not there. So you get a total. Okay, so another thing of Flower that was mentioned in the beginning when people started to implement Flower was the rate at which Flower rules were installed in the kernel and were removed in the kernel. So how much overhead does it give you to install the hardware rules versus how much time does it take the TC Flower framework to also process those things? In the beginning, a lot of the vendors had their own implementation, not really upstream. They would just hack about and just add their filters or add their hardware filters straight in OVS. So just would put some hooks there and just do it that way. And they would see way higher numbers from flow insertion and deletion rate than we would see with the TC Flower implementation. So upstream, a lot of activity has been going on to improve the number. And I think it's currently at a number where it's high enough for most of the cases. Mainly because what we see is that the bottleneck in adding the rules is not really at the open vSwitch level, but it's more at the controller level, because it takes some time for a controller to catch a missed packet and then decide it needs a specific OpenFlow rule installed in the system. So in general, we are okay. Reasons why it might be different if you have a network with a lot of different connections set up, with a high connection setup rate, and you really would like to track every single connection, because then you need to get a rule for every specific connection in your network, because you might want to do billing maybe at a very granular level. I think what's still going on is what they're looking at is batching. So now that we send one TC rule at a time to the kernel to be installed, and I think they're looking at batching them. So if you say, let's say you send a batch of 10 of them to the hardware, it might speed up as well your performance. And then the NIC vendors are also looking at changing their firmware to either install the flows faster or acknowledge the flows installation faster, so that you get a higher setup rate. If it would work. Oh, there you go. So this is a slide that shows the insertion rate of the TC rules. So what we did here was we tried to insert 40,000 TC Flower rules into a system in a loop. And we would measure how long it will take with perf to receive the call in the kernel and acknowledge that the rule was installed. So the red line is the delete, so that's pretty fast for deleting the flows. Inserting the flows, we have two lines. So the green line, that is the one where we have the skip hardware flex. So basically we only put the rule in software. And then you see, once we enable the hardware, it gets a bit slower because the hardware also needs to program the ASIC and then wait for a response to come back. But it seems to grow linearly, so even if we add more flows, it's still growing the same rate. You can see 40K is roughly around 0.85 seconds to get 40K rules in the system. Okay, let's see what my next slide was. Okay. So what is the solution that was chosen by Open vSwitch to integrate the TC Flower in their environment? So it looks a bit like the same picture with the NIC still there, but the data path and the control path is a little bit different. So the NIC on the bottom talks directly, or maybe I should go the other way around first. So OVS, let me see what is the best. No, let's start at the bottom. So if a packet comes in on a physical port, which is not known to the system, it will take the exception path. It needs to be sent out to OVS to actually have your rule installed. So what happens, it's sent up through this interface from the switch interface directly to OVS. I'm trying to see the arrows, but I don't care. Here you go. So the misses go to TC, go to the kernel. The TC path doesn't exist either, so it will probably send up directly to the OVS data path, and then the OVS data path will send it to OVS as a miss. And then OVS, what it will do, it will start programming the flow. So it will talk to the TC framework, it will install the flow in the TC framework, and then the TC framework will pull that hardware rule to the NIC. And from that way onward, traffic is just forwarded as it is. If for some reason you decided that the rule is not in hardware, the rule will still come up to the TC data path. But if you have done the skip software flag, it will still take the OVS data path and then go up or go back to the interface that way, depending on what the rules are. So why this, if the hardware cannot have the rule for some reason, you can choose the TC data path for the forwarding, so it can go TC and out, or you can do the kernel data path. The reason why they decided that they still want to go with the OVS data path as a preference is that it takes longer for the TC data path to do all the modifications and sending out the traffic, and then it takes the kernel OVS data path. So if you configure things up, you probably want to say skip software for the TC data path, and then if there's an exception for some reason, it's going to get sent there. That's what they have. So how does it work? So there is a global configuration option within OVS. So if you enable the global option, it will be sent, all the traffic will be offloaded by trying to apply the TC filter rules. And if the TC filter rules are not valid, they will take the normal kernel data path. So how is it implemented within OVS is what they do. They have hardware offload functions defined in the NetDev device for OVS. So those are all the general offload functions that you could think of. So configuring a flow in the hardware, delete a flow in the hardware. It also has the option for dumping the flows. So you can dump the hardware flows if you really want to. And that's all done at the NetDev layer within the system. And then the functions finally get called on the datapad interface, so at the DPF provider. So when actually you are programming the normal datapad kernel flows, what it does, it decides if it wants to install the TC rule, if you have it enabled, and then it will install the TC rule. If that is failing, installing the TC rule, then it will fall back to the system. So, but it's done at the datapad. So in this case, it's done at the same level as you would normally have the kernel datapad program the flows. So what happens there is will be like a mask-based flow. So it will be a wide flow that gets programmed into the system. at the same thing. So there is one level for all flows, a single table for everything. The only small difference there is that in the TC Flower solution, it doesn't allow you to have the same mask, have the same ether type with different masks at the same priority level. So what they've done in OVS is the only difference between the datapad flows, roughly, and the normal flows is that they, the normal flows and the TC flows is that they use the priority field in that case. So for the TC rules, if they see they have a different mask, they will just assign a different priority. But that's not because the traffic needs to be overlapping, but it's because of the mask or overlap. Okay. This is just a picture from the architectural overview of OVS itself, just to show you where the things are. So the NetDev provider is here. It controls the interface. So that's where it's put the OpenFlow rules there, the programming of the rules there. But they are actually called here. So when the normal data path was about to be programmed here, it will take the callback from the NetDev provider to program the TC rule in the system. This way, they can have different approaches as well. So if they decide to go away from TC or have a different approach, a different way to program the hardware, they could just replace the TC part, the callbacks there. Quickly going over some of the commands by enabling it. So it's disabled by default. If you want to enable it, you have to do it globally. Just set the hardware offload to true. And then there is 3 options to configure the policy. So by default it's none, which means it's programming both the software and the hardware for the Flower rules. Most of the hardware vendors have done their tests, and they say if you really want to take advantage of the software data path, that you should do skip software. So you should program the skip software so that the flows that are not matching by hardware are still processed the old way. So they're processed by the kernel data path, because it's a better performance there. Then some things on dumping. So if you are troubleshooting your system and you want to get the data path flows installed, if you do the normal dump command, you'll get all the flows. So you get the flows installed in the data path and the flows installed in the TC Flower data path. These commands actually, you can separate them. So if you would like only to see the offloaded TC data paths, or if you only want to see the normal OVS data path rules, this is a way to see it. Sometimes it's useful for troubleshooting to see what's there. Okay, so the next slide, or the final 2 slides I have, is what is the difference between the hardware offload performance and the DPDK performance that we compare it with. So this is a picture from one of the vendors. You can see with roughly about the same 10 packet range, or even 1,000 packet range, we are at 9 million packets per second, compared to the 4 million packets per second for using 2 cores. So it's still about only twice the speed. But on this specific blade, it probably can be higher because this is the bottleneck roughly on their PCI bus. Because the packets we do ingress and egress of the packets going to the physical interface and then out the same physical interface, every packet hits the PCI bus twice. So roughly they would get, the PCI bus gets about 18,000 packets a second. On this hardware platform, they should be able to get 25 roughly, is that. Also, there is a bit difference in the way the virtual machine acts, because in the DPDK scenario we had 2 queues. So we had 2 PMD threads pull it, so basically 2 CPUs pulling the data off the bus. In this scenario, we have 1 virtual function with a single queue. So only 1 core in the virtual machine is pulling it. So if we probably add another VF and another core, the number would probably scale to the maximum value of this specifically. Yeah, there we go. So this is the same picture, but this is with the 40 gig line. This is a 40 gig blade. So you can see even with this, it's not getting anywhere close to the 40 gig range for the smaller packet sizes. In this scenario, due to the PCI bus limit, but roughly around 500, we're hitting 40 gig wire speed with this blade. But I think the most important part in this scenario is the CPU utilization. The two graphs on the right are way too high. That's a bug in the driver that is pulling the hardware too often to get statistics. So you should probably ignore it. But this is what you should get. So here at the bottom, so roughly about 10 to 20% CPU usage due to keeping the flow stats and everything up to date. So it does take a bit of CPU, but not as much as the DPDK solution where you get half the packet size. I'll show a comparison graph later. So this is the comparison graph between the 9 million packets per second and the DPDK best performance rate, so with the 10 flows. And you can see the difference is double here. And it gradually evens out here because this is the max 10 gig rate, and probably in this picture it will be better to see. So this is the 40 gig reference line, and this is the 10 gig reference line. So you can see that on DPDK is about 400 packets we hit wire speed. For 40 gig it's a bit higher, 50 gig, but you can see it's a big advantage. And I think the big advantage shows here. So this is the CPU utilization of the DPDK solution where we have 2 cores dedicated, so it's 200% CPU utilization. Compared to whatever we have on DPDK, you can hardly see it's about 1 or 2% here in the same scenario. So I think the benefit really comes to you need a lot of less CPUs in your environment, especially because now we scaled up only to do 4 million packets per second, but if you want to do more, you're going to at least have double the number of cores dedicated. So I think that's where the real benefit is of the hardware uploads. But once again, if you're really interested in doing these things, you should really benchmark it in your setup, because I think that's the most important thing to do, because vendors can tweak whatever they like to get their best numbers, but it's always important to get your best numbers. So make sure your VMs are as you have, your CPUs are configured as you would like them to be configured. So I think that's it. So any more questions? No questions? Yeah, go ahead.
Which vendors support it? Which NIC vendors support this TC Flower?
Okay, so the question is which NIC vendors support TC Flower? So there's a couple of them. So there's Mellanox supporting it. There is Netronome supporting it. Broadcom is, I think they're working on it. I'm not sure it's really supported. There is KVM has some solution for it. What's the other one? KVM, Liquid.io, I think, Chelsea-O. So there's a lot of vendors that actually are working on getting it supported upstream. Yeah, go ahead.
Given your example was effectively the trivial case of just using TC Flower to redirect incoming traffic to a specific VM, which is by default the standard SR-IOV case. How does performance compare to just using SR-IOV?
Just SR-IOV? Yeah. I have not actually, to be honest, I haven't tried it. I haven't tried the numbers to see. I think the main difference is the speed that the packet forwarder, their classifier is working. And what I've seen, it's pretty fast. So that's part of the thing. But yeah, you lose some speed there because they need to do the classification, and there will be a little bit of latency as well in that thing. But I have no numbers. I've not tried it, to be honest. No more questions? I think that's it. Thank you.